At the end of the 19th century, physics stood at a strange and confident crossroads. To most scientists of the time, the universe appeared largely understood. The laws of motion formulated by Isaac Newton had ruled for more than 2 centuries, explaining everything from the fall of an apple to the movement of planets. James Clerk Maxwell's equations had unified electricity, magnetism, and light into a single elegant framework. Together, these theories painted a picture of nature that was smooth, continuous, predictable, and beautifully ordered. Many leading physicists believed that the remaining work of science was simply to refine measurements and calculate details to a higher degree of precision. The foundations, they thought, were complete. This sense of completion created an atmosphere of intellectual comfort, but also quiet danger. When a scientific field believes it has reached its final form, it becomes less prepared to recognize deep contradictions. Beneath the surface of confidence, small cracks were already forming. Experimental techniques were improving rapidly, allowing scientists to measure physical phenomena with unprecedented accuracy. These measurements began to expose inconsistencies between theory and reality, especially in areas involving heat, light, and radiation. At first, these problems were seen as minor technical issues, not signs of a fundamental breakdown. One of the most troubling challenges arose from the study of thermal radiation. When an object is heated, it emits electromagnetic radiation, and the color and intensity of this radiation depend on temperature. A piece of iron glowing red, then orange, and finally white as it heats, is a familiar example. Physicists sought to describe this behavior mathematically, hoping to derive a universal law that explained how energy is distributed across different wavelengths of light. This problem was not merely academic. It was central to understanding energy, matter, and the interaction between radiation and atoms. Classical physics approached this problem using well-established principles. Energy, according to classical thought, could vary smoothly and continuously. An object could emit any amount of energy at any frequency without restriction. When scientists applied these assumptions to thermal radiation, they developed formulas that worked reasonably well at low frequencies. However, as the frequency increased, the equations predicted something absurd. The energy output would rise without limit, implying that hot objects should emit infinite energy at very short wavelengths. This result, later called the ultraviolet catastrophe, was not just wrong, it was physically impossible. The ultraviolet catastrophe represented a direct collision between theory and experiment. Laboratory measurements clearly showed that radiation intensity rises to a peak and then falls off at higher frequencies. Nature behaved in a restrained and orderly way, while classical equations exploded into infinity. This was not a small error that could be fixed by adjusting constants or improving experimental technique. It was a fundamental failure of the underlying assumptions of classical physics. At first, physicists tried to patch the problem. Some introduced empirical formulas designed to fit experimental data without worrying too much about theoretical justification. These formulas worked, but they felt unsatisfying. Physics, at its core, seeks not just to describe what happens, but to explain why it happens. The gap between mathematical description and physical understanding grew wider, and the discomfort among thoughtful scientists increased. This crisis was especially unsettling because it struck at the heart of determinism. Classical physics was built on the idea that if you know the present state of a system precisely, you can predict its future with certainty. Energy flowed smoothly, causes led directly to effects, and randomness was merely a sign of incomplete knowledge. The failure to explain radiation suggested that this world, you might be incomplete or even wrong at a deep level. Yet abandoning it seemed unthinkable to many. Into this tense, intellectual climate stepped Max Planck. He was not a revolutionary by temperament. He admired classical physics and believed deeply in the absolute validity of physical laws. Planck valued order, logic, and mathematical beauty, and he was reluctant to embrace speculative ideas. Ironically, this conservative mindset made the crisis even more disturbing for him. He was not searching for a new physics. He was trying to save the old one. Planck focused intensely on the radiation problem, particularly the behavior of an idealized object known as a blackbody, which absorbs and emits radiation perfectly. By studying experimental data and exploring various mathematical approaches, he attempted to derive a formula consistent with both theory and observation. For years, progress was slow and frustrating. Each classical approach eventually led back to the same contradictions. What made this period critical was not just the technical difficulty, but the psychological tension it created. The most trusted theories of nature were failing, yet no clear alternative existed. Physics was balanced on the edge of a conceptual cliff. The invisible assumptions that had guided scientific thought for centuries were being questioned by stubborn experimental facts. This was the true crisis of classical physics, not a single failed equation, but a growing realization that nature might not conform to human expectations of continuity and certainty. The crisis extended beyond radiation. Other phenomena also resisted classical explanation. The stability of atoms posed a serious problem. According to classical electromagnetism, electrons orbiting a nucleus should continuously radiate energy and spiral inward, causing atoms to collapse. Yet atoms were stable. Spectral lines emitted by elements appeared at precise frequencies rather than forming a continuous spectrum, another hint that energy behaved in a discrete manner. These clues were scattered across different areas of research, but they all pointed toward a deeper issue. Despite these warning signs, many physicists remained confident that classical physics could eventually overcome these challenges. The history of science had shown that temporary contradictions often led to refinement, not revolution. Few suspected that an entirely new framework would be required. The crisis was real, but its implications were still largely unrecognized. This tension between confidence and confusion defined the scientific atmosphere of the era. It was a moment when the invisible foundations of physics were under strain, when established laws no longer matched the world they were meant to describe. The stage was set for a profound transformation, though almost no one could see it clearly at the time. The importance of this crisis lies not only in its technical details, but in what it reveals about scientific progress. Science does not advance smoothly in a straight line. It moves through periods of stability interrupted by moments of deep uncertainty. These moments force scientists to confront the limits of their understanding and to question assumptions that once seemed unquestionable. The crisis of classical physics was one such moment, a turning point where the old picture of reality began to crack. In this fragile and uncertain environment, Max Planck would make a decision that changed everything. But before that decision could be made, physics had to reach a point where its existing tools no longer worked. The failure of classical physics to explain radiation was not just a problem to be solved. It was a signal that the invisible structure of nature was far stranger than anyone had imagined. This realization marked the beginning of a journey into the quantum world, a journey that would redefine science, technology, and humanity's understanding of reality itself. This first keynote, The Crisis of Classical Physics, is therefore not simply a historical backdrop. It is the essential starting point of the quantum revolution. Without this breakdown, there would have been no need for new ideas, no reason to challenge continuity, and no opening for the concept of quanta. The invisible world did not reveal itself easily. It forced its way into human awareness through contradiction, failure, and doubt. And it was precisely this crisis that made discovery possible. If you want, next I can continue with Part B, the remaining 2,500 words in the same documentary-style flow without headings. As the crisis deepened, the sense of unease within the physics community slowly intensified. What made the situation especially troubling was that the failures of classical theory were not isolated incidents. They appeared again and again in different experiments, in different laboratories, and under different conditions. Each time, the same pattern emerged. The mathematics was elegant, the logic was sound, yet nature refused to cooperate. This growing mismatch between expectation and reality forced a quiet but profound shift in how some scientists viewed their discipline. Many researchers continued working as if the problem were temporary, believing that a clever adjustment or a missing term in an equation would restore harmony. Others began to suspect that something more fundamental was wrong. The idea that the universe might not be fully continuous, that energy and matter could behave in unfamiliar ways, was unsettling. It challenged not only scientific theories, but also philosophical beliefs about causality, predictability, and order. Physics was no longer just about calculating forces and motions. It was beginning to question the very nature of reality. The laboratories of Europe became places of tension as well as discovery. Precision instruments recorded results that could not be ignored. The data was consistent, repeatable, and stubbornly resistant to classical explanation. This was especially true in the study of radiation, where improvements in measurement revealed fine details that older experiments had missed. The more carefully scientists observed nature, the less it behaved according to the rules they trusted most. This period revealed an important truth about science. Experiments are the final judge of theory. No matter how beautiful or logically complete an idea may seem, it must answer to observation. Classical physics, for all its success, was failing this test in critical areas. The crisis was not dramatic in a public sense. There were no sudden announcements or immediate revolutions. Instead, it unfolded slowly through papers, debates, calculations, and long nights spent trying to reconcile equations with evidence. Max Planck felt this tension deeply. He was driven by a belief that the laws of physics reflected absolute truths about the universe. To him, the idea that these laws might break down was almost unbearable, yet he was also honest enough to follow the evidence wherever it led. This internal conflict between loyalty to classical ideas and commitment to empirical truth mirrored the broader struggle within physics itself. As Planck continued his work, he became increasingly aware that traditional assumptions were blocking progress. The belief in continuous energy, once seen as self-evident, began to look like an obstacle rather than a foundation. Still, abandoning it felt like stepping into darkness. There was no established alternative, no guiding framework to replace it. Any departure from classical thinking risked confusion and criticism. The crisis also exposed the limits of human intuition. Classical physics aligned closely with everyday experience. Objects move smoothly, energy seems to flow continuously, and causes appear to produce predictable effects. But the experiments probing radiation and atomic behavior operated far beyond the scale of ordinary perception. The invisible world was not obligated to behave in ways that felt comfortable or familiar. This realization was slow to take hold, but once it did, it changed the direction of scientific thought. What made the situation even more complex was the success of classical physics in so many other areas. Planetary motion, engineering, optics, and mechanics continued to work flawlessly within classical frameworks. This partial success made it harder to accept that the theory might be fundamentally incomplete. It was not failing everywhere, only in specific and puzzling domains. This selective failure raised a troubling question. Could a theory be both correct and incorrect at the same time, depending on the scale or conditions? The answer to that question was not yet clear, but the crisis forced physicists to consider it seriously. It suggested that nature might operate according to different rules at different levels, and that classical physics might be an approximation rather than a final truth. This idea was radical, even disturbing, but it offered a way forward. Instead of trying to force all phenomena into one framework, scientists could begin to explore where and why certain theories applied. The invisible pressure of this crisis reshaped scientific attitudes. Younger physicists, less emotionally invested in classical traditions, were more willing to explore unconventional ideas. Older scientists often resisted, clinging to familiar principles. This generational tension added another layer to the unfolding transformation. Physics was not just changing intellectually, it was changing culturally. The struggle also highlighted the role of humility in science. The confidence of the late 19th century had been built on extraordinary success, but it had led to a sense of completion that was ultimately false. The crisis served as a reminder that no theory, no matter how powerful, is beyond revision. Nature does not conform to human pride, and understanding advances only when scientists are willing to admit uncertainty. As the limitations of classical physics became undeniable, the stage was fully prepared for a breakthrough. The failure itself became a kind of guide, pointing toward what needed to change. Continuous energy, strict determinism, and absolute predictability were no longer untouchable assumptions. They were hypotheses to be tested and possibly replaced. This moment in history shows how scientific revolutions are born not from sudden inspiration alone, but from prolonged discomfort. The crisis of classical physics created an intellectual vacuum, a space where new ideas could emerge. Without this breakdown, there would have been no reason to question continuity, no motivation to imagine energy behaving in discrete steps. The invisible world was demanding a new language, one that could describe its strange and subtle behavior. Classical physics had taken humanity far, but it had reached the edge of its explanatory power. The realization of this limit was both frightening and liberating. It marked the end of certainty, but also the beginning of deeper understanding. In this sense, the crisis was not a failure of science, but a success. It demonstrated that scientific knowledge is not static. It evolves through challenge, contradiction, and revision. Each breakdown opens the door to a more refined view of reality. The collapse of classical explanations for radiation did not destroy physics, it transformed it. By the time Max Planck introduced his radical assumption, the ground had already been prepared by years of unresolved problems and growing doubt. The world of physics was ready, even if it did not yet realize it, to accept an idea that would change everything. The crisis had done its work. It had stripped away false certainty and exposed the invisible complexity of nature. This period stands as a powerful reminder that the most important discoveries often begin with failure. When trusted ideas no longer work, when equations refuse to match experiments, and when confidence gives way to confusion, science is at its most alive. The crisis of classical physics was such a moment, a turning point where the visible order of the universe gave way to a deeper, stranger, and more profound reality waiting to be discovered. Max Planck's struggle to explain Blackbody radiation did not begin as a quest for fame or transformation. It began quietly, almost reluctantly, rooted in a sense of duty to physics itself. At the turn of the 20th century, Blackbody radiation had become one of the most stubborn problems in science. A blackbody, an ideal object that absorbs all incoming radiation and emits energy solely based on its temperature, seemed simple in concept. Yet, when physicists tried to describe its behavior mathematically, simplicity vanished. Experiments were becoming increasingly precise. Heated cavities with small openings allowed radiation to escape in a controlled way, producing detailed spectra that could be carefully measured. These measurements revealed a clear pattern. At low frequencies, radiation intensity increased with frequency. At higher frequencies, it peaked and then declined sharply. This behavior was consistent, repeatable, and undeniable. Nature was speaking clearly. The problem was that classical physics could not understand the language. Planck watched as others proposed solutions that only partially worked. Some formulas fit the low-frequency region, others fit the high-frequency region, but none explained the full spectrum. Each attempt felt like a compromise rather than a true explanation. To Planck, this was deeply unsatisfying. Physics, as he understood it, was not about stitching together convenient answers. It was about uncovering universal laws rooted in fundamental principles. What made the problem especially painful for Planck was his philosophical commitment to determinism and continuity. He believed that physical processes followed strict, unbroken laws, and that energy flowed smoothly, not in jumps. This belief was not just scientific, it was personal. Planck saw the laws of nature as reflections of deep order and rationality. To question continuity felt like questioning the coherence of the universe itself. For years, Planck worked tirelessly, applying every classical tool he trusted. He explored thermodynamics, statistical mechanics, and electromagnetism, searching for a derivation that would naturally produce the observed radiation curve. Again and again, his calculations led to dead ends. Each failure forced him to confront an uncomfortable truth. The assumptions he relied on might be the very reason the problem remained unsolved. The pressure was not only intellectual but emotional. Planck was a careful, disciplined thinker, and he disliked speculative leaps. Yet the data demanded something new. Experimentalists were no longer content with rough agreement. Precision demanded precision. The gap between theory and observation narrowed until it became impossible to ignore. Planck's isolation during this period is often overlooked. While other physicists explored bold ideas more freely, Planck remained cautious, almost burdened by responsibility. He did not want to introduce a hypothesis that lacked solid grounding. He feared that abandoning classical principles would lead physics into chaos rather than clarity. This inner conflict slowed him, but it also made his eventual break, through more profound. As months turned into years, Planck began to reconsider the role of probability and statistics. He turned to the ideas of Ludwig Boltzmann, whose statistical interpretation of thermodynamics had been controversial. Boltzmann suggested that macroscopic laws emerged from the collective behavior of microscopic entities. governed by probabilities rather than certainties. Planck had long been skeptical of this approach, but desperation forced him to take it seriously. Using statistical reasoning, Planck attempted to describe how oscillators in the walls of a blackbody cavity exchanged energy with radiation. Still, classical assumptions about continuous energy exchange led to incorrect results. The equations stubbornly returned to the same divergence at high frequencies. It was as if the mathematics itself was pushing back, refusing to comply. The turning point came not as a moment of inspiration, but as a reluctant concession. Planck realized that if he assumed energy could only be exchanged in discrete amounts, the calculations suddenly worked. The radiation curve emerged naturally, matching experimental data across all frequencies. The mathematics was elegant, precise, and shockingly effective. Yet Planck was deeply uncomfortable with this assumption. He did not see it as a statement about reality, but as a formal trick, a mathematical device to make the equations behave. To him, the idea that energy itself was quantized felt unnatural, almost absurd. Nevertheless, the success of the result could not be denied. This internal struggle is crucial to understanding Planck's achievement. He did not embrace quantization with enthusiasm. He accepted it with reluctance, driven by the evidence rather than ideology. This makes his discovery all the more powerful. It was not born from speculation, but from surrender to experimental truth. When Planck presented his findings, the response was muted. Many physicists viewed the quantization assumption as an oddity, useful perhaps, but not fundamental. Even Planck himself did not fully appreciate its implications. He believed that a deeper classical explanation would eventually be found, one that would restore continuity and determinism. But the seed had been planted. By allowing energy to be emitted and absorbed in discrete packets, Planck had crossed a boundary that could not be uncrossed. The blackbody radiation problem, once a source of frustration and failure, became the doorway to a new understanding of nature. This struggle reveals the human side of scientific discovery. Progress does not always come from bold visionaries eager to overturn tradition. Sometimes it comes from careful thinkers pushed beyond their comfort zones by stubborn facts. Planck's greatness lies not only in what he discovered, but in how he discovered it, through persistence, honesty, and a willingness to let evidence outweigh belief. The blackbody radiation problem forced Planck to confront the limits of classical physics and his own convictions. It demanded a sacrifice, the abandonment of an assumption so deeply ingrained that it had shaped centuries of thought. In making that sacrifice, Planck did not just solve a problem. He opened a path into the invisible world of quanta, a world that would soon reshape science forever. This is only the first half of that journey. In the second part, the consequences of Planck's reluctant decision begin to unfold, spreading far beyond blackbody radiation and transforming the foundations of physics itself. When Planck released his radiation formula to the scientific world, he did so without drama and without any claim that it represented a new vision of reality. To him, it was a solution to a stubborn technical problem, not a declaration of revolution. Yet beneath this modest presentation lay a profound shift that would soon ripple through physics. The idea that energy could be exchanged only in discrete amounts, no matter how reluctantly introduced, carried implications that could not remain contained. At first, the scientific community treated Planck's result with cautious respect rather than excitement. The formula worked remarkably well, matching experimental data with a precision no previous theory had achieved. This alone earned it attention, but not acceptance at a deeper level. Many physicists believed that the quantization assumption was a temporary placeholder, something that would eventually be replaced by a more complete classical explanation. The history of physics had taught them that strange hypotheses often disappeared once better mathematics or improved understanding emerged. Planck himself shared this expectation. He continued to view continuity as the true nature of energy and regarded quantization as a formal step rather than a physical statement. In his mind, the discrete packets were a feature of the calculation, not of the universe. This hesitation mattered because it slowed the immediate philosophical impact of his work. The revolution did not arrive overnight. Instead, it crept forward quietly, carried by the undeniable success of the mathematics. As other physicists began to examine Planck's formula more closely, they noticed something unsettling. The constant that appeared in his equation, later named Planck's constant, had the dimensions of action, linking energy and time. It was not an arbitrary fitting parameter. It seemed to encode a fundamental scale of nature. The presence of such a constant suggested that there might be a smallest meaningful unit of energy exchange, a limit beyond which classical ideas no longer applied. This realization made some scientists uneasy. Classical physics had no room for such limits. In its world, nature was infinitely divisible. Any quantity could be made smaller, any change more gradual. Planck's constant stood in quiet opposition to this belief. It hinted that the microscopic world might be governed by rules that imposed boundaries where none were previously imagined. The Blackbody radiation problem, once considered a narrow technical issue, now appeared in a new light. It was not just a failure of calculation, but a window into deeper structure. The walls of a heated cavity, once treated as simple oscillators exchanging energy continuously, now seemed to participate in a more constrained dance. Energy was not flowing freely, it was stepping. Despite this growing awareness, resistance remained strong. Many physicists argued that quantization applied only to the interaction between matter and radiation, not to radiation itself. Others suggested that the discreteness arose from the properties of the oscillators, not from energy as a fundamental concept. These distinctions allowed scientists to use Planck's formula, while postponing uncomfortable conclusions. What kept the idea alive was not philosophical persuasion, but practical success. Planck's law did what no other theory could do. It worked everywhere. In laboratories across Europe, experimental data confirmed its predictions again and again. Each confirmation made it harder to dismiss the quantization assumption as a mere trick. The true turning point came when the problem escaped its original boundaries. The quantization idea began to appear in contexts far removed from Blackbody radiation. When Albert Einstein applied Planck's concept to explain the photoelectric effect, he took a bold step that Planck himself had hesitated to take. Einstein suggested that light itself behaved as if it were made of discrete energy packets. This move shocked the physics community, but it also provided a clear explanation for experimental results that classical wave theory could not handle. Planck watched these developments with mixed feelings. On one hand, he recognized the power of the idea he had introduced. On the other, he was uneasy about how far it was being pushed. The notion that light, long understood as a wave, could also behave like particles challenged deeply held assumptions. Yet the evidence continued to accumulate, and resistance slowly weakened. The struggle over Blackbody radiation thus became a struggle over the meaning of physical law. It raised questions about whether theories describe reality itself or merely organize observations. Planck's initial caution reflected a broader scientific humility. He was aware that equations could succeed without revealing the full truth. But as quantization spread into other areas, it became increasingly difficult to maintain a purely instrumental view. This period illustrates how scientific change often unfolds. New ideas rarely arrive fully formed or immediately accepted. They enter quietly, solving specific problems, and only later reveal their broader significance. Planck did not set out to discover the quantum world. He stumbled into it while trying to rescue classical physics from collapse. In doing so, he demonstrated how progress can emerge from loyalty rather than rebellion. The emotional dimension of this struggle is also important. Planck's discomfort did not vanish once his formula was accepted. He lived through the early years of quantum theory, witnessing the rise of ideas that challenged determinism, certainty, and even causality. While he accepted these developments intellectually, they never fully aligned with his philosophical instincts. His experience reminds us that scientific revolutions are lived by individuals, not just recorded in textbooks. Over time, the Blackbody radiation problem faded from prominence, replaced by broader questions about atoms, electrons, and waves. Yet its role as a catalyst remained. It was the first clear signal that classical physics could not describe the microscopic world. It forced a reconsideration of energy, matter, and interaction at the most fundamental level. Looking back, it becomes clear that Planck's struggle was not just about finding the right formula. It was about facing the limits of human understanding. He stood at the boundary between two worldviews, one rooted in continuity and certainty, the other pointing toward discreteness and probability. His reluctance did not weaken his contribution, it strengthened it. Because he resisted change, the change he finally accepted carried enormous weight. The Blackbody radiation problem thus occupies a special place in the history of science. It marks the moment when physics stopped assuming that nature must conform to human intuition. It showed that reality could be stranger, more fragmented, and more subtle than centuries of experience had suggested. Through careful work, intellectual honesty, and reluctant courage, Planck helped reveal this truth. In the end, his struggle teaches a lesson that extends beyond physics. Progress often begins when we acknowledge that our most trusted ideas may be incomplete. It requires patience to endure uncertainty and integrity to accept uncomfortable conclusions. Planck did not celebrate the breakdown of classical physics, but he did not deny it either. By choosing evidence over belief, he allowed a new understanding of the invisible world to emerge. The quantum revolution did not begin with a shout. It began with a quiet adjustment in an equation, made by a man who wished it were not necessary. Yet from that adjustment flowed a transformation that reshaped science, technology, and our view of reality. The invisible world of quanta entered human knowledge not through bold speculation, but through the careful struggle of a physicist unwilling to ignore what nature was trying to say. The birth of the quantum idea did not arrive as a sudden announcement or a clear philosophical declaration. It emerged quietly from the tension between mathematical success and conceptual discomfort. When Max Planck introduced the assumption that energy could be exchanged only in discrete amounts, he did not present it as a new picture of reality. Instead, it appeared almost as a reluctant compromise, a way to make theory agree with experiment. Yet within this modest step lay the beginning of a radical transformation in science. Planck's proposal marked the first time that continuity, a cornerstone of classical physics, was deliberately set aside. For centuries, energy had been treated as something that could vary smoothly, taking on any value without restriction. By suggesting that energy came in fixed packets, Planck challenged this deeply rooted belief. These packets were not arbitrary. Their size was determined by a new constant of nature, linking energy to the frequency of radiation. This relationship was simple in form, but profound in meaning. What made the quantum idea especially strange was that it did not arise from direct observation. No one could see these energy packets or measure them individually at the time. They were inferred from the way nature behaved as a whole. This was a new kind of scientific reasoning, one that accepted invisible structures as real because they made sense of observable facts. The quantum idea was not intuitive, but it was effective. At first, the idea lacked a clear physical interpretation. Even Planck viewed it as a mathematical assumption rather than a statement about how the world truly worked. Energy quantization seemed like a rule imposed on calculations, not on nature itself. This ambiguity slowed acceptance, but it also allowed the idea to survive. Physicists could use the concept without fully committing to its implications. The true significance of the quantum idea became clearer as it began to explain other phenomena. When Albert Einstein applied it to light, he proposed that electromagnetic radiation itself behaved as if it were made of discrete units. This bold step transformed Planck's cautious assumption into a physical principle. Light, once thought to be purely wave-like, now exhibited particle-like behavior under certain conditions. The quantum idea had escaped its original context and begun to reshape fundamental concepts. This expansion revealed that quantization was not an isolated trick, but a general feature of nature at small scales. Atoms, long mysterious in their stability and spectral behavior, suddenly made more sense when energy levels were treated as discrete. Electrons could occupy only certain allowed states, and transitions between them produced radiation of specific frequencies. The quantum idea provided a unifying explanation where classical physics had offered only puzzles. The emergence of this idea also transformed the goals of physics. Instead of seeking exact trajectories and continuous motions, scientists began to focus on allowed states, probabilities, and transitions. The emphasis shifted from certainty to structure, from smooth change to discrete possibility. This was not merely a technical adjustment, but a conceptual shift in how reality was described. The birth of the quantum idea illustrates how revolutionary changes in science often begin modestly. There was no grand manifesto, no immediate rejection of classical physics. Instead, a single assumption, introduced for practical reasons, gradually revealed a deeper truth. Its power lay not in its philosophical clarity, but in its ability to explain what had previously seemed inexplicable. Over time, the quantum idea forced physicists to accept that the microscopic world operates according to rules unlike those of everyday experience. Energy, once seen as endlessly divisible, was revealed to have a grain-like structure. This insight opened the door to quantum mechanics, a theory that would redefine matter, light, and information. In retrospect, the birth of the quantum idea stands as one of the most important moments in scientific history. It showed that reality could not be fully understood through intuition alone, and that nature often demands new ways of thinking. What began as a reluctant mathematical assumption became a gateway to the invisible world, forever altering humanity's understanding of the universe. The idea of energy as discrete packets marked a decisive break from the smooth, flowing picture of nature that had dominated physics for centuries. In classical thinking, energy was like water in a river, able to change continuously, taking on any value without restriction. Max Planck's proposal replaced this image with something far less intuitive. Energy, at least at the microscopic level, behaved more like a staircase than a slope, changing only in specific steps. This shift did not merely adjust existing theory, it redefined what energy itself meant. At the heart of this idea was the realization that energy exchange depends on frequency. Planck showed that the energy emitted or absorbed by microscopic oscillators was proportional to the frequency of the radiation involved. This relationship introduced a new constant of nature, one that set the scale for these energy packets. The existence of such a constant suggested that the universe had a built-in limit to how finely energy could be divided, a concept that had no place in classical physics. What made this concept so challenging was its invisibility. These packets of energy could not be seen directly, nor could their individual effects be isolated with the experimental tools of the time. Their existence had to be inferred from collective behavior, from patterns in radiation spectra and thermal distributions. Accepting discrete energy meant trusting mathematics and experiment over intuition, a difficult step for many physicists. The packet-like nature of energy also introduced a new kind of constraint. Physical systems could no longer change in arbitrary ways. Only certain energy values were allowed, and transitions between them occurred abruptly rather than gradually. This explained why atoms emit and absorb light at specific frequencies rather than across a continuous range. The sharp spectral lines observed in experiments were no longer mysterious. They were direct consequences of quantized energy levels. This view transformed the understanding of stability in nature. In classical models, systems often appeared unstable at small scales. Electrons orbiting a nucleus, for example, should continuously lose energy and collapse inward. Quantized energy levels prevented this collapse by restricting the allowed states. Stability emerged not from smooth balance, but from discrete permission. Systems remained stable because there were no intermediate states into which they could decay. The idea of energy packets also reshaped the concept of interaction. Energy transfer became an all, or nothing process at the smallest scales. A system either absorbed or emitted a full packet or did nothing at all. This helped explain why increasing the intensity of light did not always produce stronger effects, while increasing frequency could. The behavior of light and matter no longer depended solely on quantity, but on structure. As this concept spread, it became clear that quantization was not limited to radiation alone. Mechanical vibrations, atomic motion, and later even fields and forces were found to obey similar rules. The discrete nature of energy appeared as a universal principle, hinting at a deeper architecture underlying the physical world. Reality at its core was not smooth and continuous, but granular and structured. This insight forced physicists to rethink measurement and prediction. Classical equations described continuous curves, but quantum behavior required new mathematical tools. Probabilities replaced certainties, and exact values were replaced by allowed ranges. The discrete packet became the fundamental unit around which new theories were built. The acceptance of energy as discrete packets was not immediate or easy. It required letting go of familiar images and accepting a reality that could not be visualized in ordinary terms. Yet once embraced, it provided clarity where confusion had reigned. Phenomena that once seemed unrelated now shared a common explanation. In the end, the concept of discrete energy packets revealed that the universe has an underlying rhythm, a smallest beat that governs change at the microscopic level. This rhythm cannot be subdivided endlessly. It defines what is possible and what is forbidden. By uncovering this structure, physics moved closer to understanding the invisible rules that shape the visible world. When the idea of quantized energy first entered physics, it did not arrive to applause or immediate acceptance. Instead, it was met with hesitation, doubt, and in many cases open resistance. The scientific world, at the beginning of the 20th century, was deeply invested in classical principles that had proven extraordinarily successful. To many physicists, the suggestion that energy behaved in discrete jumps rather than flowing continuously seemed not only strange, but unnecessary. Classical physics had explained so much that abandoning its core assumptions felt reckless. One major source of skepticism was philosophical. Classical physics aligned closely with everyday experience and long-standing beliefs about causality and continuity. Motion appeared smooth, change appeared gradual, and effects seemed to follow causes in a predictable way. Quantization threatened this world, by introducing abrupt transitions and fixed limits where none were expected. For many scientists, this was not just a technical issue, but a challenge to how reality itself was understood. Another reason for resistance was the lack of direct evidence. No one could observe energy packets in isolation. The quantum idea relied on indirect inference from experimental results, which made it feel abstract and speculative. Physicists were accustomed to grounding theories in concepts that could be visualized or measured directly. The invisible nature of quanta made them difficult to accept as real entities rather than mathematical conveniences. Even Max Planck, the originator of the idea, shared much of this skepticism. He did not initially believe that energy was truly quantized in nature. To him, the assumption was a formal step, a way to force agreement between theory and experiment. This cautious attitude influenced how others received the idea. If its creator hesitated to interpret it literally, why should the broader community rush to embrace it? There was also concern about consistency. Classical physics formed a coherent, interconnected system. Mechanics, thermodynamics, and electromagnetism supported one another through shared assumptions. Introducing quantization threatened to disrupt this harmony. If energy was discrete in one context, where did discreteness stop? Could classical laws still be trusted elsewhere? These questions raised fears of fragmentation rather than progress. Debate and criticism followed. Some physicists attempted to explain quantization as a property of matter rather than energy itself. Others hoped that future refinements would eliminate the need for discrete assumptions altogether. Many treated the quantum idea as a temporary tool, useful but ultimately replaceable. This cautious approach allowed research to continue without forcing immediate philosophical change. Despite the resistance, evidence slowly accumulated. Experimental results continued to align with predictions based on quantization, while classical explanations failed repeatedly. Each successful application made dismissal more difficult. The idea survived not because it was comforting, but because it worked. A turning point came when younger scientists began to adopt the concept more boldly. Less bound by tradition, they were willing to explore its implications without apology. As quantization proved useful in explaining atomic spectra, heat capacities, and later chemical behavior, skepticism weakened. The resistance did not vanish overnight, but it gradually transformed into cautious acceptance. This period of doubt and debate highlights an important feature of scientific progress. New ideas are not judged solely on correctness, but on how well they fit existing frameworks and beliefs. Resistance is not necessarily a flaw. It acts as a filter, demanding strong evidence before change occurs. In this case, Skepticism forced the quantum idea to prove itself repeatedly. The initial rejection of quantization also reveals the human side of science. Scientists are not detached observers. They are shaped by education, intuition, and philosophical commitments. Letting go of deeply held beliefs is difficult, even when evidence points elsewhere. The struggle over quantization was as much about mindset as mathematics. In the end, resistance did not stop the quantum revolution. It slowed it, tested it, and ultimately strengthened it. By surviving intense skepticism, the idea of discrete energy emerged more robust and better understood. What was once seen as a disturbing anomaly became a cornerstone of modern physics, reminding us that the path to new knowledge often passes through doubt before reaching acceptance. Once the idea of quantization began to take hold, its role quickly expanded beyond solving a single problem. What started as an attempt to explain Blackbody radiation grew into the foundation of an entirely new framework for understanding nature. The sixth keynote, The Foundation of Modern Quantum Physics, marks the moment when isolated insights began to connect, forming a coherent picture of the microscopic world. The acceptance of quantization allowed physicists to rethink the structure of atoms. Classical models could not explain why atoms were stable or why they emitted light at precise frequencies. With quantized energy levels, these mysteries found clear explanations. Electrons were no longer free to occupy any orbit or energy state. Instead, they were confined to specific, allowed levels. Transitions between these levels produced radiation with well-defined frequencies, directly matching experimental observations. This framework transformed the atom from a classical miniature solar system into a structured quantum object. Stability emerged not from continuous balance, but from restriction. Atoms remained intact because there were no permitted states between energy levels. This insight reshaped chemistry as well as physics, explaining why elements have distinct properties and why chemical reactions follow predictable patterns. As quantum ideas spread, they began to influence the understanding of matter itself. The behavior of solids, liquids, and gases could now be explained in terms of quantized vibrations and energy distributions. Phenomena such as specific heat, electrical conductivity, and magnetism revealed underlying quantum rules. Classical physics still worked at large scales, but its limits were now clearly defined. The mathematical language of physics also changed. New equations were developed to describe systems where classical trajectories no longer applied. Instead of predicting exact positions and velocities, quantum theory described probabilities and wave-like behavior. This shift was not a retreat from precision, but a recognition that precision took a different form at small scales. Certainty was replaced by statistical structure. One of the most profound consequences of this foundation was the unification of previously separate ideas. Light and matter, once treated as fundamentally different, began to share common principles. Both exhibited wave-like and particle-like behavior depending on context. This duality challenged intuition, but provided a powerful explanatory tool. The foundation of quantum physics also redefined measurement. Observing a system was no longer a passive act. Measurement itself influenced outcomes, introducing limits to what could be known simultaneously. This was a radical departure from classical thinking, where observation simply revealed pre-existing properties. The act of measurement became part of the physical process. Despite its strangeness, quantum theory proved extraordinarily successful. Its predictions matched experiments with unprecedented accuracy. From atomic spectra to subatomic particles, quantum principles provided reliable results where classical methods failed. This success cemented its status as a foundational theory rather than a temporary solution. Importantly, quantum physics did not discard classical physics entirely. Instead, it placed it within a broader context. Classical laws emerged as approximations that applied at large scales or high energies. This layered understanding preserved past achievements while extending their reach. The foundation laid by quantum physics also opened new technological possibilities. Understanding energy levels and quantum transitions made it possible to design devices that harnessed microscopic behavior. Electronics, lasers, and modern computing all trace their origins to these principles. The theory did not remain abstract, it reshaped everyday life. Perhaps the most enduring impact of this foundation is philosophical. Quantum physics forced humanity to reconsider notions of reality, determinism, and knowledge. It revealed a universe that is not fully predictable, yet deeply structured. Order exists, but it is expressed through probability rather than certainty. The sixth keynote represents the moment when the quantum idea matured into a complete framework. It was no longer an isolated concept or a controversial assumption. It became the language through which the invisible world was described. In laying the foundation of modern quantum physics, scientists did more than solve equations. They discovered a new way of seeing the universe, one that continues to shape science and thought today. The lasting impact of Max Planck's discovery reaches far beyond the moment when the idea of quanta first entered physics. What began as a solution to a narrow scientific problem gradually transformed the way humanity understands nature and the way modern civilization functions. The seventh keynote, The Lasting Impact on Science and Technology, reveals how an abstract idea about energy reshaped both knowledge and daily life. At the scientific level, Planck's work permanently altered the direction of physics. By introducing quantization, he opened the door to a deeper exploration of the microscopic world. Entire fields emerged from this foundation, including quantum mechanics, quantum field theory, and solid-state physics. These disciplines did not merely add details to existing theories. They redefined what it meant to explain physical phenomena. Concepts such as wave-particle duality, uncertainty, and probability became central to understanding reality at its smallest scales. The influence of quantum theory spread quickly into chemistry. The behavior of electrons within atoms explained the structure of the periodic table, the nature of chemical bonds, and the rules governing reactions. Without quantum principles, the stability of molecules and the diversity of matter would remain unexplained. Modern chemistry, from pharmaceuticals to materials science, rests on ideas that trace directly back to Planck's original assumption. Technology provides the most visible evidence of this lasting impact. Devices that define modern life depend on quantum behavior. Semiconductors, which form the basis of computers and smartphones, rely on controlled energy levels within materials. Lasers, used in medicine, communication, and industry, function through stimulated emission, a purely quantum process. Even medical imaging techniques and precision measurement tools are built on quantum principles. Beyond current technologies, Planck's discovery continues to shape the future. Quantum computing aims to exploit superposition and entanglement to perform calculations beyond the reach of classical machines. Quantum communication promises unprecedented security through the fundamental laws of physics. These emerging technologies demonstrate that the quantum revolution is not complete. It is still unfolding. The impact of quanta also extends into philosophy and culture. By challenging determinism and certainty, quantum theory altered how scientists and thinkers view knowledge itself. Reality appeared less rigid and more subtle than previously believed. This shift influenced debates about free will, observation, and the limits of human understanding. Planck's work helped move science away from the illusion of absolute predictability toward a more nuanced vision of order. Education and scientific practice were transformed as well. Physics curricula changed to include quantum concepts as foundational rather than optional. New generations of scientists were trained to think in terms of probability, abstraction, and mathematical structure. Research methods evolved to accommodate phenomena that could not be directly visualized, emphasizing inference and indirect evidence. Perhaps the most remarkable aspect of Planck's legacy is how a reluctant discovery became indispensable. He did not seek to overturn classical physics, yet his work revealed its boundaries and extended its reach. The idea of quanta did not replace classical laws. It explained when and why they apply. This layered understanding remains a model for scientific progress, showing how new theories can encompass old ones rather than destroy them. On a human level, Planck's impact lies in the example he set. His willingness to accept uncomfortable conclusions in the face of evidence reflects the deepest values of science. He demonstrated that truth matters more than personal preference or philosophical comfort. This attitude continues to inspire researchers across disciplines. The lasting impact of quanta is thus both practical and profound. It shapes the tools we use, the theories we trust, and the questions we ask. From the smallest particles to the largest technologies, the influence of Planck's insight is woven into the fabric of modern civilization. In revealing that energy itself has structure, Max Planck helped humanity glimpse the invisible order beneath the visible world. That glimpse grew into a revolution whose effects continue to expand. More than a century later, the world of quanta remains a source of discovery, innovation, and wonder, proving that a single idea, born from careful struggle, can change the course of history.